Hi everyone. So for this project, I had the opportunity to interview Professor Bowen, whose lab does research using various types of spectroscopy and spectrophotometry to study the fundamental electronic structures of clusters and nanoparticles. His research has been used to solve a multitude of problems today in the scientific fields of biology, chemistry, and astrophysics. The goal of my project is to explore the applications of spectroscopy and build off of our knowledge from studying the hydrogen emission spectra in Lab C. More specifically, I hope to answer the question, how can spectroscopy be applied to chemical compounds outside of hydrogen which we already investigated? And what properties of chemical compounds can we deduce from using spectroscopy? How can these discoveries be applied to modern technology and innovations today? First, I'll start with a quick overview of what we've learned in class. In Lab C, we looked at the hydrogen emission spectra using a spectrophotometer to determine at what wavelength the transitions between energy levels occur. We focused on the Rydberg equation and different spectra of hydrogen, for example, the Lyman series and the Balmer series. We also learned about the photoelectric effect, which is a fundamental process underlying the idea of photoelectron spectroscopy. The photoelectric effect is essentially the phenomenon in which electrons are released from or within a material when it absorbs enough electromagnetic radiation. In my interview with Dr. Bowen, he introduced photoelectron spectroscopy and its applications to understanding the fundamental structures of negatively charged and neutral clusters and nanoparticles. He described that anion-based photoelectron spectroscopy is typically used to study the sample's electron affinity. On the other hand, his experiments on neutral samples using photoelectron spectroscopy are typically done to determine the sample's ionization energy. The photons shot on these samples typically are ultraviolet rays, since it takes a large amount of energy to remove electrons from a neutral atom. He describes this as a violent process. Sometimes UV rays don't provide enough energy to eject an electron, and X-rays must be used. Dr. Bowen first discussed how to find the binding energy of an electron with a very straightforward equation shown on the screen.
Photoelectron spectroscopy is all based on the photoelectric effect. You want to know the electron binding energy. You know the photon energy. You measure electron kinetic energy, and because this is such a pure, exact equation, then what you end up getting is a peak that corresponds to that transition and one that corresponds to that transition.
As Dr. Bowen mentioned, since the kinetic energy and photon energy are known, the equation can easily be rearranged algebraically to find the electron binding energy. On a molecular level, once UV light is absorbed, an electron from the outer orbital, in this case the 2p orbital, leaves the molecule. The kinetic energy of this electron can be measured and determined by the spectrophotometer. In this way, photoelectron spectroscopy can measure electron kinetic energy, binding energy, and orbital energies, depending on what is plotted and what intensity of light is used. The binding energy can be plotted against intensity, with peaks corresponding to different transitions. An example of such a graph is this one from a publication from the Bowen lab discussing a spectroscopic and computational study of deprotonated gallic acid. Binding energy is a necessary value to know in order to calculate the energy needed to split a particle from a system of particles, such as electrons bound to nuclei or atoms and ions bound together in crystal lattices. Photoelectron spectroscopy, as we learned in class and from Dr. Bowen, is used to determine, detect, and quantify the fundamental properties of molecules, such as their structure, magnetic properties, and electronic properties. This allows us to understand the foundational characteristics of atoms and structures to analyze the reactions they can participate in to advance in research and science today.